Hello, this is the final presentation for ME452 Team 7. My name is Sam, and we have Alex, Blake, Maggie, Patrick, and me here on this team. We'll be discussing the analysis and redesign of a thermoelectric cooler, which was actually a team member's 450 project. The product, which can be seen in the CAD models here, aims to cool small spaces. It takes in air and redistributes the cool air to one side and the hot air to the other. 4 thermoelectric chips, shown here in yellow, are sandwiched between 2 heat sinks, which are connected to 2 couplers and 2 fans. All of these components are held together through the casing. As a brief recap, the assembly sequence of the product is shown here, where the part numbers correspond to the order of assembly. The green parts represent the platform parts, or the parts common for product variants, while the red parts represent the modules, or the parts that are different for product variants. Parts 7, 8, and 9 make up the thermoelectric subassembly, which is assembled separately together before insertion into the product. The primary customer is any low-resource person hoping to cool small spaces. The secondary customer is anyone looking for an inexpensive way to regulate the temperature of a small space. The team also brainstormed that it could be used at the central bus hub on campus to keep students warm or cool, and even have a filtration system to fight against COVID or other diseases.
After completing a functional analysis, we decided that the primary function of this device is to either cool or heat a person, depending on the customer group. To perform this primary function, the device needs to push and guide air, or draw air, as well as change temperature by cooling the air or heating the air. Further, to assure dependability, the device must prevent burns, lacerations, and electrocution. Finally, along with enhanced product and police senses, to assure convenience of this device, it needs to control velocity and collect condensation. Our function component mapping matrix has the terminal nodes of our fast diagram in the top row, and the components are the leaves from the fishbone diagram. Note that the casing provides the structure and assures dependability, and the electronics assembly includes the electronic components and the housing. Also note that the fans and the couplers both draw the air.
To aid in product family design, we categorized all of the parts of the product into either being part of the platform or to be varied as modules in differentiation. Majority of the parts in the platform are integral to the operation of the heating and cooling of the airstreams. And for the modules, we have the left and right sides of the casings, as well as the cold side coupler to be varied depending on the customer group. Next, we categorize the various functives of the product to be same for both customers or different for each customer group. In the column that's same for both customers, we see that a lot of these are safety related, as well as basic functions, cooling and heating air, and collecting the condensation that can occur from the cooling process. Drawing air is different for each customer group due to the hot side coupler changing to match the cold side coupler. Lastly, the filter air functive has been added corresponding to the addition of a filter.
Another secondary product variant is the casing color. This design change would enable users to select between certain available colors, such as in the picture, where we show a red case on the left and a blue case on the right. The choice of color would add cost to the product, but we believe the secondary customer group would be willing to pay more for the added benefit. One of our design changes to accommodate the secondary customer group was to add a product variant where both couplers were cylindrical. This way, both couplers could be connected to an outlet hose, allowing the customer to leverage both the hot and cold sides for thermal management.
The manual assembly time for the original product was found to be 140.84 seconds with an assembly efficiency of 0.26. The product platform was redesigned such that the cold and hot side fans will be affixed to the casing via snap fits instead of screws. Further, the casing, which is a module part, was changed to incorporate the hot side coupler, reducing the part count of the product. Leveraging design guidelines DFAS1, DFPI3, DFJ1, and DFJ3, the final assembly time was found to be 96.34 seconds with an assembly efficiency of 0.37. Automated assembly was considered for the thermoelectric subsystem, which consists of the hot and cold side heat sinks and the 4 thermoelectric chips. The original design consisted of the 4 chips being clamped together via the 2 heat sinks using 4 screws. This design was found to have handling and insertion costs of 12.24 cents and 14.5 cents per part, respectively. Upon redesign, the screws were replaced with thermal adhesive compound placed on either sides of the 4 thermal chips, holding the subsystem together. Leveraging design guidelines DFAS1, DFAS3, and DFJ1, the final handling and insertion costs were reduced to 8.64 cents and 13.5 cents per part, respectively.
Here is the process selection matrix for the casing and hot side coupler combination part. We use criteria such as shape, mass, section thickness, tolerance, surface roughness, and economic batch size to determine which of these processes would be best. Ultimately, we selected injection molding out of the two that we narrowed down to machining and injection molding. Here is the process selection matrix for cold side coupler part. Again, we use shape, mass, section thickness, tolerance, surface roughness, and economic batch size as criterion to select the process. We were able to narrow it down again to machining and injection molding and selected injection molding for this part.
For the design for manufacturing section, our first selected part was the left-hand casing with a total cost estimation using the equation reviewed in class for a plastic injection molding part of $36.6 per part. Assuming that the right-hand casing is symmetrical, the total cost estimation is also $36.6 per part too. On the other hand, the hot round coupler total cost estimation is $8.68. Therefore, these three parts of assembly has a total cost of $81.88. Three of the features we can do for a redesign could be the merging of half of the hot round coupler into each casing to avoid an extra part, DFAS number 1, minimize part counts. The reduction of the nominal wall thickness from 2.5 mm to 2 mm, DFIM number 1, minimize wall thickness. The reduction of the number of side pulls making the bends in the same die vector, DFIM number 6, avoid side pulls. Finally, we can also increase the number of parts produced from 10,000 to 15,000 parts. After all these design modifications, these two parts of assembly has a total cost of $61.38. This means that with these design changes, we can have a cost savings of $20.5.
Another part of our product that we were able to redesign to result in manufacturing cost savings was the coupler and casing subassemblies. For our product differentiation, one of our products, the cold side coupler, has a square output and the other has a round output. This allows for a tube to be attached for the round if desired. Originally, we had two different casings and two separate couplers. As you can see here, they resulted in each subassembly costing around $87. So we redesigned the round coupler to have a square interface with the casing, so that the square coupler and the round coupler are both compatible with the square casing. As you can see, this resulted in pretty large savings of around $30, which is just under a third of the original cost. This is largely due to the fact that we completely eliminated the round casing and we're able to produce more parts with the square casing. We're producing relatively low numbers of parts for injection molding, and so the majority of the cost for these parts comes from the cost of the mold, and by eliminating the round casing, we're able to completely eliminate a mold that we had to create. Since more restaurants are offering outdoor dining due to COVID, a potential product service system could be renting out multiple units as either coolers or heaters for the customers. Unlike current heating options, our product does not require filters or propane to run, reducing maintenance. Additionally, since they can cool or heat customers, they're more flexible. And we could offer these units as a rental service, which would reduce environmental impact, as you only buy them when you need them. You don't have to throw them out afterwards.
Ultimately, we have two product variants, one that allows for only cooling and one that allows for both cooling and heating. After redesigning the thermoelectric cooler, we cut down on parts, reduced assembly complexity, and added delayed differentiation. This led to a reduction in cost. Despite this, the product is still relatively expensive, and its use of materials like plastic is not very environmentally friendly. Moving forward, the product design could be greatly improved by making changes to the size and geometry of the product to create smaller design with features that are easier to manufacture. Analysis of sustainability and environmental impact can also be done.